Hello everyone, and welcome to my presentation. My name is Catalina, and I'm a PhD student at Eindhoven University of Technology. And together with the team, we are very pleased to be able to present you the work titled Improving the Flexibility of 5G Heterogeneous Networks by Slicing. I will start the presentation by introducing 5G and the Internet of Things ecosystem. And next, the motivation for having a flexible 5G network and why should slicing be employed. And then I will continue with the introduction to network slicing, followed by a few research directions that are planned to be verified in our future 5G deployments. And finally, the conclusions and a few words about the focus of my research. I will start by introducing the 5G networks. So 5G is the adapted solution that aims to fulfill the demanding requirements for high data rates and low latency. Moreover, 5G is set to support diverse user scenarios and applications for new use cases with a wide range of requirements. On the right-hand side, we can see three types of such scenarios. On top of the pyramid, we can find enhanced mobile broadband, where the main goal is to achieve high throughput. On the right is ultra-reliable, low-latency communication, where stringent requirements for low latency are the main target. And on the left of the pyramid, there is massive machine-type communications, where the use cases are characterized by a huge number of connected devices. Having in mind these scenarios, if the IoT ecosystem is efficiently integrated in the 5G infrastructure, the users can have access to dedicated services with a small delivery time, and the mobile operators could benefit from reduced expenses. These dedicated services can be provided to the end users through a flexible network, and in order to achieve that, and to meet the 5G performance indicators, we need multiple technologies like software-defined networking, network function virtualization, multi-access edge computing, and artificial intelligence techniques as highlighted. As mentioned earlier, the new IoT services will be increasingly demanding in terms of latency or availability of real-time data. And at the same time, the IoT devices will generate a big amount of data. In order to cope with this, it is essential to design and deploy a decentralized service platform architecture based on MEC that brings the computing and storage resources closer to the end users, which in the end can lead to enhanced quality of service and quality of experience. On the right-hand side, MEC is represented together with the 5G user plane function, but this is only an example. One of the main advantages of MEC is its flexibility in terms of deployment, but we will discuss more about this in the next slide. So we have all these requirements and enablers, but how can a service be efficiently managed? Or more exactly, how can a particular service with specific requirements for the control and user plane be managed? The answer, or at least one of the answers, is network slicing. In this slide, the 3GPP approach for network slicing will be presented, but in order to do so, I will start with what is network slicing. A network slice is the possibility of creating a virtual data pipeline virtual data pipelines on top of a shared physical infrastructure for every type of service. As represented on the right-hand side, when a user equipment registers to the network, it signals its network slice preference by providing a parameter called single network slice selection assistance information, S and SSAI. It is important to mention that a UE may be connected to up to 8 network slices simultaneously, which means that it can establish up to 8 PDU sessions, but the set of network slices to which a UE is connected may change dynamically. The selection of network slices that the UE is allowed to use can be made either by access and mobility management function, the AMF, or with the support of the network slice selection function, the NSSF. Both of them are control plane functions in the core network. But in order to access the data network, session management function and user plane function, the UPF, are also involved in the process. All right. Previously, we mentioned that the UE expresses its slice preference through S and SSAI. The S and SSAI is comprised of two parts: the slice service type, the SST, and the slice differentiator, the SD. Based on 3GPP, SST can have values from 1 to 5, depending on the service type, like EMBB, URLC, MIT, vehicle to everything, or high-performance machine type communications. One thing to mention is the SD, that SD complements SST to differentiate amongst multiple network slices of the same slice service type. In the following two slides, I'll present some research directions that will be considered for our next 5G and edge computing implementations. The first direction considers the different deployments of the G0B centralized unit and distributed unit. In the first scenario, the CU control plane is centralized and can coordinate several DUs, and the CU user plane is centralized to provide a central termination point for user plane traffic. A benefit for this type of deployment is that the CUCP and the CUUP can be implemented in a virtualized environment. In the second scenario, as seen here in the middle, CUCP is deployed in a distributed manner and collocated with the DU, while the CUUP is centralized. In this case, the CUUP can be virtualized and low latency can be ensured for critical control plane procedures. In the third scenario, as seen here on the right, CUCP is centralized, able to coordinate multiple DUs, while CUUP is distributed. The benefits here can be that the radio coordination from CUCP side. This is one of the benefits: the radio coordination from the CUCP side, and lower latency from the user plane traffic. The second direction targets the flexible deployment of MEC. For example, one option can be MEC and UPF collocated with the G0B. Another option, as seen here in the middle, can be MEC collocated with the core network functions, or as seen here on the right, MEC and the local UPF collocated with the network aggregation point. The option can vary for sure, but measuring the performance and analyzing the security issues that each implementation can bring are the things that can apply for every type of scenario. Next, the third direction considers the similarities between MEC and NFV. Both concepts embrace a virtualized architecture, so the idea of using the NFV environment for MEC deployments can be used as a reference when trying to merge new functions. This idea was proposed by Etsy, and introduces the possibility of deploying MEC platform and applications as virtual network functions. In the figure, the red lines represent the new reference points, MV1, MV2, and MV3, introduced between elements of the ETSI-MEC architecture and the ETSI-NFV architecture to support the management of mobile edge applications. With the close connection between UPF and MEC, the idea of deploying the user plane function in a similar manner as described earlier as a virtual network function can be possible. There are some clear advantages of this implementation, which concern the decrease of latency, therefore the network response is provided faster, or the reuse of infrastructure, but there is no clear answer whether the already known functionalities of network function virtualization infrastructure, the NFVI, or the virtual infrastructure manager, DV, or other virtualization blocks need to be changed. Next, with the current transition to MEC, one of the open questions is whether the application function from the core network can be eliminated. An argument against the elimination of the core network function is its support for the other core network functions, and this may bring significant changes in the current implementations. However, in the current approach, it may disappear since each slice is supposed to have an UPF, therefore a MEC environment connected to it. This means that the application function responsibilities will be distributed in the entire network. Last direction targets the employment of artificial intelligence techniques for a faster slice selection. Having this big volume of data can be a great resource since when creating training or testing datasets, which means that challenges brought by the 5G heterogeneous networks like traffic optimization or network pattern predictions can be solved faster. To conclude, we can summarize the presentation with the next ideas. The end users can benefit from dedicated services while attached to a slice-based 5G network. MEC, with its flexible deployment at the edge, NFV, with the hardware and software decoupling, and SDN, with the user plane and control plane decoupling, are the technologies that can facilitate the implementation of 5G slicing. Users can have access to a wide range of services mapped to different slices by providing the SNSSAI. We can say also that virtualization can ease the integration of different network functions. And here we have seen MEC and NFV integration example and the idea of integrating the user plane function in the architecture. And last point, AI can be employed for a faster slice selection, given the big amount of data from the IoT devices and the new challenges that come with the increased connection density. Before ending the presentation, I would like to say a few words about my research area, which is mainly focused on the edge computing integration with the 5G communication, where I am mainly targeting computational flooding and 5G security. Also, I am one of the 15 early stage researchers that are part of the IoTalentum project, and also part of the quantum key distribution testbed team here at TU Eindhoven. And with this, I would like to say that I will be happy to connect or discuss future collaboration. So thank you for your attention. If you have any questions,